All right, so start off a review here. Let's talk about this limit problem. Yeah, we did several types of limits along the way. The ones where we had x going to a number, there were several techniques. Sometimes we used factoring, sometimes we did the conjugate. This one is one of the others, a different one. This one here, if this is just a nice, I guess you might say, a nice way of writing a complex fraction, because 6 to the negative 1, that's going to flip over and be 1 over 6 to the positive 1, and then this will be 1 over 2x to the positive 1. So, like I said, this is just a nice way of writing really what it is. It's a complex fraction. And when we had those complex fractions, what we did is we tried combining the numerators, remember? The fractions in the numerator. Get a common denominator. In this case, the LCD of those would be 6x. And so make both of those have denominator 6x. So what we do, all right, so to make this denominator, I'd have to multiply by x. So on top by x as well. Then this one, to make it 6x, I need to multiply by 3 in the denominator, so I multiply the numerator as well by 3. And so that gets me common denominators. Yeah, so now I've got common denominator on the top, so I can combine those numerators, basically. Now the other thing here, let's go ahead and condense this now. All right, so this is what I'd have on the top. This means divide by x minus 3, right? If I wrote it that way, it would have to be that divide by 3, which divide by x minus 3, but that means times the reciprocal. So it'd be times 1 over x minus 3 is one way to look at that, right? So divide by x minus 3 means times 1 over x minus 3. And yeah, that's the next thing we look for is look for either factoring or something we can cancel out, which we can, because now I've got an x minus 3 in the numerator, I've got an x minus 3 in the denominator. And so that gives me the limit as x goes to 3 of 1 over 6x. Now, I didn't try substituting in at first, but usually on those, you're not going to get it to work out, because what you wind up, if I went in and substituted first, that would give me 6 to the negative 1 minus 6 to the negative 1, that would be 0, and then the bottom would be 3 minus 3, that would be 0. So I couldn't substitute in. So that's why we do these little techniques, is we can't substitute in right away. Now when we do our little thing there, we can substitute in, can't we? So that's the whole goal of this, solving these limits, is get it where we can substitute in. Now I can substitute in the x to be 3 and get my limit to be 1 over 18. All right, and so we'll come across some other ones in just a second, some other techniques, but that's one technique. Now, on number 2, here, all right, so number 2, we've got the limit as x goes to infinity, 5 minus 7x squared minus 9x cubed over 27 minus 5x squared. All right, so the limits as x goes to infinity, remember the technique we did on that to show our proof or whatever of this limit was divide the top and the bottom by the largest power in the denominator. And so in this case, I've got a larger power of x, but in the denominator I've got x squared is the largest power. So I'm going to divide top and bottom by x squared. And that's what you do for these limits as x goes to infinity. So that gets me the limit as x goes to infinity of, that'd be 5, so divide each of those by x squared. 5x squared, 5 over x squared minus, now divide that by x squared, that'll just be minus 7. And divide that by x squared, that'll be minus 9x. And then do the same, divide that by x squared, so 27 over x squared minus 5. Right? With me so far? Yeah, so that sets up some nice things. As x goes to infinity, anytime you have a number divided by x to a power, that goes to 0, right? So 5 divided by x to a power, if you're going to infinity, that's going to 0. Or 7 goes to 7. Now, this one, I just got minus 9 times x, and so as x goes to infinity, that's negative 9 times infinity. We'll deal with that in just a second. And then 0 minus 5 in the denominator, okay? So, all right, so what I have, basically what I have on top is I've got negative 7 minus infinity, and then on the bottom I've got negative 5. Well, if you take negative 7 and minus infinity, that's just going to be minus infinity, isn't it? And then we divide that by negative 5. Well, a negative infinity divided by negative 5, that's still going to be infinitely large. However, it is a negative divided by negative, and so in the end, won't it be a positive infinity? So number 2, we get infinity. I mean, it doesn't always come out to be an infinity there. Sometimes you do just get a number, but that's how you do those infinity. X goes to infinity. Any questions on that? Look okay? All right. Number 3. Find the derivative using the definition of derivative. Okay, so I probably will have one where you will have to use the definition of the derivative. Probably just one though. The others, will use the derivative techniques or derivative rules, but there'll probably be one where you have to do the definition of derivative. And so let's remember what that is. So my function is square root of 2x minus 9. All right, so the definition of derivative is f prime of x equals the limit as h approaches 0 f of x plus h minus f of x divided by h. Been a while, hasn't it? That looks familiar, hopefully. Yeah, so may have you do one like that. All right, and so it's another limit problem. Okay, so to evaluate it, for f of x plus h, that just means plug in x v h, so that would be the square root of, well, if x is x plus h, that would be 2x plus 2h minus 9. Minus then f of x, well, f of x is just the square root of 2x minus 9. That's divided by h. So this is our limit that we have to evaluate here. Which brings up another technique we talked about in evaluating limits. If we've got a square root like this, what we used was, what do we use on that? Conjugate. So we're going to multiply to get this limit. Yeah, again, I can't plug in h to be 0 yet because the denominator goes to 0, of course, obviously. So yeah, we use the conjugate. 2x plus 2h minus 9 plus the square root of 2x minus, just same two square roots, just plus between them. But we have to do that in the denominator as well. All right, so that is the limit as h approaches 0. Yeah, the nice thing, when we multiply the conjugates together, what happens there is, well, you get the square root of 2x plus 2h minus 9 times itself. And so that's going to work together and just get rid of the square root part, right? So that combined would be 2x plus 2h minus 9. The middle terms, We usually don't even write them because what'll happen is you got that times that, but then you have the minus of that. So those two will just cancel out, so we usually don't even write that. And then you'll have the minus square root of 2x minus 9 times positive square. So again, the square roots cancel out, but there is a minus sign there. So we want to be careful with that. It is going to affect those signs. And then the bottom is, of course, just leave it factored out, if you will. Don't multiply those two together, because we get a little canceling here in a second. Okay, so yeah, this is going to be, to save a little time here, this will be minus 2x plus 9. And so the 2x's are going to cancel, and then the 9's are going to cancel, aren't they? So we'll just have 2h over h as those two square roots. Yeah, but that's good because now we can cancel out that h. That h cancels with that h. And so on top we'll just have 2. And then as h goes to 0, that goes to 0, so this will be the square root of 2x minus 9. There's not an h in that, so that'll just be square root of 2x minus 9. And so what I have there is 2, and then I've got 2 square roots of square root of 2x minus 9. And last but not least, yeah, the 2's will cancel, so I get 1 over the square root of 2x minus 9. Would be the derivative for our little function there. Which we could check by use a chain rule there to check it, but I will have you go through, like I said, go through at least, I think there's just one of those, maybe not this particular one, but with the definition of derivative. But if it doesn't say you use the definition of derivative, then it's just using the rules for derivatives, which is what we have next, isn't it? Number 4. F of x equals 5x minus 4 over x squared minus 3x plus 1. All right, well, yeah, so this one's just find the derivative. It doesn't say use the definition, so we don't have to use the definition here. We just have to use the appropriate rule. All right, and so we had several rules for derivatives, right? We had the chain rule, power rule for derivatives, quotient rule, and product rule. The ones I'm recalling right now, but so yeah, those are all necessary, helpful. So we won't have to use the definition of derivative. Those rules give us kind of a quicker way, in most cases, way to find these derivatives. So this one is the quotient rule, of course, right? We've got a quotient. So let's recall it. The way I remember it, it's low d high minus high d low over low squared. So we start with the low, x squared minus 3x plus 1, and then do the derivative of the high, which the derivative of the high would just be 5. And then minus the high, 5x minus 4, times the derivative of the low, which would be 2x minus 3. And then divide that all by low squared, so x squared minus 3x plus 1 squared. Turns out is our derivative on those. And then once you get that, then you just simplify from there. 5x squared minus 15x plus 1 plus 5. Distribute the 5. Here, see, I need to FOIL. Let's FOIL that, so that would be 10x squared minus 15x minus 8x plus 12. But there's a minus in front of those, all those, so it'll be minus 10x squared. That'd be minus 23x, it'd be plus 23x, and then minus 12. You could do it 2 steps there if you want. Over the low squared, and then combine the like terms, so it'll be minus 5x squared plus 8x minus 7. Did I get that right? So okay? Good? All right. Any questions on that one? All right, number 5. See what we got there. We've got g of x equals cosine x cubed times tangent cubed x. First thing I would say about that is, yeah, that tangent cubed x, that's a nice way of writing it, but for purposes of derivatives, probably better to write it without that cube like that. Tangent cubed x means I'm taking the tangent of x and cubing it. So it's tangent x to the 3rd power. So that'll help us as far as derivatives go. All right, so find the derivative here. Well, first thing to note is we've got cosine of x cubed times that. So that's a product rule, first of all, right? Easiest one to forget, because you just want to say, well, let's do the derivative of that times the derivative of that. Well, it just doesn't work that way with derivatives. You have to alternate, rotate them doing the derivative. So the product rule first. All right, so if I do the derivative now, so also part of this, so if I do the derivative of that, I've got an inside and outside part of that, don't I? And so also involved here is our old quotient rule, isn't it? Because we've got an inside and outside part. So the quotient rule, remember how you do that is derivative of the outside times then also the derivative of the inside, right? So the derivative of this, so this is the outside, this is the inside. So the derivative of the outside is derivative of cosine is negative sine. Now when I do the derivative of the outside, what happens to the inside? It stays the same, right? So it's sine of x cubed. And then I multiply that by the derivative of the inside, which is 3x squared. And then the tangent of x cubed, I keep it as is, but you can write it either way you want there. Is that okay? So we've got, that's the first part of the product rule, which involved the quotient rule. All right. Then the second part of the product rule, well, the second part of the product rule is, since I did the derivative of this first, this second part, it will stay the same. So the second part of this product rule is cosine of x cubed times then the derivative of the tangent of x to the 3rd, which that's also a quotient rule, isn't it? I'm sorry, chain rule, because I've got an inside and outside part. Now in this case, the inside is the tangent and the outside is to the 3rd power. And so chain rule says do the derivative of the outside, so I bring down the power, make the new power 1 less, inside stays the same, but then I multiply by the derivative of the inside, which, yeah, that's, I didn't mention it, but yeah, remember those derivatives of your trig function, sine, cosine, tangent, all those. What's the derivative of tangent? Secant squared? And then let's just clean it up a little bit. Let's write that negative 3x squared times sine x cubed. And let's go ahead and rewrite that as tangent cubed x. here, I've got a 3 cosine of x cubed times secant, tangent squared x, secant squared x. So yeah, that one little function, it actually turned into quite the derivative there, but that's just the way products work. They expand quite a bit. Is that all right? Yeah, so I think we covered, at some point or another, covered all 4 of those, but the only one we didn't use, this one, was the quotient rule. We used the other 3. So. Anyway, is that all right? Okay. Number 6. Find dy dx. X cubed minus y cubed plus x squared y squared equals 4y minus 9. Yeah, so we're finding dy over dx, which that's just means the derivative of y with respect to x, so we're really doing the same thing that we're doing. However, in this case, we have a much more complicated equation, and so we used a little different technique on those. That was, remember that what we call that? The implicit differentiation. Implicit differentiation. And the way we did that was you take the derivative with respect to x of both sides, call it d dx of both sides. So I'm going to ddx this side and ddx this side, just meaning take the derivative with respect to x of both sides. Now, when I take the derivative with respect to x of x cubed, that gives me 3x squared. However, whoops, it's minus. However, when I take the derivative with respect to x of y cubed, yeah, that gives me 3y squared, but what else do I need along with that? Remember, with the y, if I'm doing the derivative with respect to x of a y, I would also need the dy over dx, right? All right, so that's kind of the catch on these. If you're doing the derivative with respect to x of a y, you got to add that dy over dx. Don't forget that. All right, then the next one, again, you got 2 parts there, x squared times y squared. And again, that's the easiest time to forget. It's a product rule, you got to do those separately, derivatives. So let's do the derivative of dx squared would be 2x. Leave the y squared alone. So 2xy squared. Then let's do the x squared times the derivative of the y squared, which would be 2y, but it's a y, we're doing the derivative with respect to x, so I need dy over dx. Okay? So all of this is because that's the derivative of that. Then the right side's a whole lot easier. The derivative of 4y would be 4, but it is a y, so I need the dy over dx. And then the minus 9 is a constant, and that's still a derivative of 0. All right. So it looks like now the next step here, well, the next step is I need to get the dy over dx is on the same side, and you can do them to the right or to the left. Or to the right, doesn't matter. Looks like in this case it'd be easier just to pull those dy over dx to the other side. So I'm going to add 3y squared dy over dx, and then subtract 2x squared y, let's call it, dy over dx from both sides. To get rid of it on this side. This side then is just 3x squared plus 2xy squared. Now this side, yeah, we've got all the dy over dx's, so I can factor off the dy over dx on that, those, and so it's 4 plus 3y squared minus 2xy. And now since that's dy over dx times that, just divide both sides by that expression. And that's our dy over dx, that's our derivative. y respect to n. All right? Sound okay? All right, let's try number 7 here. Evaluate the integral. All right, so not only did we do limits and derivatives, but we also came up with some integrals, which really the integral ties in all three. Definition of integral is it's the limit of a infinitely many rectangle, so it's a limit. And then it turned out that a lot of cases, or if you can find the antiderivative of something, that gives you your integral. So all three are involved here, those three things. But anyway, the one here, I mean, some of them are just, antiderivative power rule, that one we use a lot. But I wanted to go ahead and remind us, this one is the way we evaluate this integral is with the u substitution, right? Or substitution. Yeah, I can't do the antiderivative as is of sine of 3x minus 5, but if I let u equal 3x minus 5, and a lot of times u is the stuff on the parentheses there, in parentheses, then let's see what happens. All right, so then that makes this du, so you also need du, which is the derivative of that, which is 3 times dx. And the way I usually do it is solve for dx here, so divide by 3. So du over 3 is dx, and so that's what I'll substitute for dx in my integral. So if I make those substitutions, I'll have sine of u du over 3, which is just 1/3 sine of u du. Well, I know something about the antiderivative of sine of u. The antiderivative of sine of u is just it's negative cosine. So this would be negative 1/3 cosine of u. And since this, don't forget, this is an indefinite, so we need the plus c there. And then finish it off, go ahead and back substitute, go back in and substitute the 3x minus 5 for u. So that's a pretty simple one, but wanted to do one with the u substitution. A lot of times on the u substitution we'll get, like when we do the substitution of du, we'll get some cancellation of the x squared. Sometimes there's some other things we have to do, but anyway, we wanted to give you a reminder there of u substitution. Probably a couple of those.